plan for presenting because I still cannot reach my desktop back in Michigan, although the internet is back. So I wrote a new one and I try to relate it as much as possible. The framework I work in, I'm a MHD modeler. In Michigan, we use the space weather modeling framework, in which the solar model is the alpha wave solar atmosphere model. It's awesome. Short for it. It's a fully 3D MHD model. It models plasma from the transition region out to the termination shock. You have the only input is a radial magnetic field at the inner boundary, and you run your simulation. It's very few free parameters. Basically, there is one that we sometimes vary, which is the Poynting flux on the base that's hitting the plasma, and two other that is solar cycle dependent. Let's just say that. So it's a physically self-consistent. Coronal heating and solar wind acceleration is due to low frequency alpha wave turbulence. We calculate isotropic electron and parallel and perpendicular proton temperatures relative to the magnetic field. Radiative losses, collisional and collisionless heat conduction, instabilities due to the temperature and isotropy, proton-electron heat exchange are all addressed in the model. And recently, we added non-equilibrium ionization of heavy ion charge states up to zinc from the P&T tables. And we can calculate these ionization distributions for the heavy ions throughout the 3D domain, not only along follow lines, both in time-dependent and steady-state mode. So some of the model outputs are here. Oh, this is, yes, laser pointer. Yeah, so you have a 3D plasma data, so you can compare it to in situ measurements. You have EUV observations. You can do spectral imaging, and you can do line spectra. Yes. So, of course, we validated our code against the HINODI observations. You see that it's based on if you look at a closed field region or you look at a coronal hole, you match better or worse. Some lines are missing from Chianti, so that we could not model, but it's not far from what is observed. So what OSAM can do? So as I mentioned, that is, I think, not obvious. So we have 2 and 3 temperature simulations. Both of them can be fed to this spectral calculation. Doppler shift, thermal broadening, distinction between observed and theoretical lines are possible. You can add instrumental broadening. You can make composite of using narrowband image response functions. You calculate line broadening due to alpha wave fluctuations, which is relative to the observer's location and the angle of the B field. And as I mentioned, non-equilibrium ionization of heavy ions is channeled into the spectral and narrowband image calculations. And we also have photo excitation, so we can handle lines with comp and ucomp. So what it means is the line, that what we do with the line broadening. So in the model, we use alpha wave energy densities that are calculated as a state variable. That means that we can actually estimate the B fluctuations. Also could be, I think, compared to comp observations along magnetic fields or plane cuts or integrated around the line of sight. So thermal broadening takes into account the angle that we are looking at, which is important for heavy ions well, actually, it's a bit higher, I think. So above the 2 solar radii point of view, where you have a strong temperature and isotropy observed, for example, in oxygen lines. And also using the alpha wave energy densities, we calculate the non-thermal broadening that is here, and then we add the instrumental broadening, and this is how we build up our emission lines. So what is new relatively, and I think that is I haven't seen it on I don't know, like in relation to comp observations, is taking into account the ion distributions. So what we do in Awesome is that we solve the MHD. So parallel, we solve the non-equilibrium ionization of heavy ions parallel to the MHD solution. And our abundances are fixed, so you cannot look at like line ratios between different elements. But within the same element, for example, this is a carbon 6:5 ratio that's compared to the Ulysses measurements of the third flyby. Green is simulation, black is observation. It matches pretty well the observation. So you can look at distributions of ionization levels within one element. And how is this affecting our spectral imaging and overall remote sensing? So this figure is a line of sight integrated observation of 171. We can do exactly the same with comp lines. I just don't have access again to those data. So you can look at any line, basically, calculate the emission considering equilibrium ionization and non-equilibrium ionization. And here I show the ratio that tells you that at coronal holes and the streamer legs, you have a significant difference that you introduce as expected, up to even 100%. You can also decompose this emission change on this figure between red is 1.2 and blue is 0.8. I show that how considering non-equilibrium charge states changes the emission relative to the equilibrium solution in a meridional plane on a 0.2 solar radii sphere around the solar body, and also on selected field lines. So not only you can look at the integrated images, but you can also decompose that where that change is originating from. So one thing that I think the modeling support can do is this, that you can not only decompose via the line of sight, but also you can decompose physical processes that happen. And of course, these all channel into the narrowband imaging. So when someone is doing, for example, DM calculations using these imagers, you have to think about that. You might be inputting errors of like 40% by assuming that your emission is coming from equilibrium ionization. And also, if you look at that for the same channel but two different instruments, of course, you have a completely different sensitivity that depends on the regions and yes, etc. So this is a comparison to comp observation that so for me it's a bit painful that I can't have like a direct intensity calculation. I mean that I can't have like units. So I don't know if I should. I'm looking for inputs if I should do the same thing, that I take the average from the disk so I don't know how to normalize my units the same way that I could get something similar.
Well,
maybe
the intensity is not a physical unit anymore. It's an image that has been passed through structures.
So how could I make reasonable comparisons? That's beyond
the. Want to use the intensity, not the intensity.
Oh,
that one is in meters.
Okay. Yes.
And if you can, and I'll show you and forward. I've got it set up to change units. So standard that's on the web, I think, is in parts per million, but it sure forward. Certainly with the synthetic data, you can take your data and intersect with that and change the parts per million to compare.
Okay.
I'm not sure I've got it going the other direction. Where I can change comp into any units. I've got like unit drop down.
Okay.
Yeah,
Okay.
These said there are a couple of caveats. We have a difference in the intensity and continue curve, still that we don't quite understand. And also we are reprocessing
Mhm.
the data in 2012 because it was probably a bit diffuser. So all the comp data. So if you are interested in this particular phase, let us know and we can give you the best
Mhm.
we can do. But there is still an unknown difference between comp and your program. I don't know if you want to comment.
Right. I think the simple answer to your question is you multiply our numbers by the intensity of the solar disk from like an atlas.
Mhm.
Something, you know, and units of photons per arc second squared
Okay.
centimeter per second. And that
And
will,
then I will get it back. Okay.
Yeah, and that's all that
Multiply by-
forwards to.
Okay.
10 our numbers, because they're per million, so there's a 10 to the 6th. That
Okay.
needs to be applied, and that's it.
Okay.
I mean, that will, and use the solar, solar intensity outside the atmosphere. So
Yeah. So for me, it would be very,
maybe that's too simple an answer.
very. Yeah. That's. I thought it's something very complicated going on. Yes. So you can, so what I said, decompose effects. You can take off the photo excitation of different lines and see that how much they affect for the same image. And also you can do 3D decomposition. I went back to 171. So this is the field lines are colored with the radial speed, the electron temperature, and here I show that how the different ions freeze in like along the field lines. And this is again so this is a map of emission at the 1.2 solar radii sphere, and the field lines are also, and the meridional plane I colored with this emission. So I think that this also could be useful to see that where strong emissions are coming from. Like this one, you see that it's like the strongest emission is actually coming from behind the plane of sky or on the top, etc. But yeah, so. And why I'm keep saying this? So this is an integrated intensity image. This is the width of the line, and this is the Doppler map. So with comp you don't see the disk, so you don't see this huge jump, and maybe you don't get suspicious that what is this big red shift doing here. But if you look at the data in a cut plane, so we just took a cut from the center here and look at the side at what is the actual data come from, how we integrate, this is along the line of sight now, X, then you see that you have a stronger emission coming from a streamer just behind the South Pole. So actually what you see here as a strong emission is absolutely not coming from where you think. It's unrelated to the polar magnetic field completely, but that is so dominant that you don't see anything else in this integrated image. Yes, and this is my mission, so I'm sorry that I bore everyone with this. The peak temperature is not equal to the temperature where the plasma emits from. I'm showing here two isosurfaces that emit with the same intensity, like intensity density basically, and I colored them with electron temperature. The peak formations cover like most, so you see that it's around, yeah, so here is the peak formation temperature, and but you can see that from like 1 to 2 million Kelvin, the same amount of emission is coming from all over this isosurface area. So I would be very careful to associate line observations with one temperature. That's my mission. And what I'm trying to use, I originally tried to use comp for, and now it will be ucomp, is that reconstructing the coronal magnetic field. So the idea is that we have a very strong dependence in our model of the observed radial magnetic field that is in the single input, basically. So I was wondering if we could use comp data to correct it in an iterative way, that we add a weak random noise to the magnetic field, to the boundary on the top of the measured magnetic field, and see if our next solution is converging to the comp observation, and iterate until it does and matches up to a certain point. And our model would be perfect for this because, as I showed you, we can calculate emissions on individual magnetic field lines. So the emission strengths are well integrated in the line.
Question.
Yes.
So to what extent do you have, so it's non-potential, right? It's got currents in it.
Yes.
But to what extent do you think you could add currents that won't be reflected in your adapt boundary condition, which is line of sight, and which is, I mean, because there's currents in the corona that exist, which you can't usually do with that kind of boundary condition. But, there's sometimes ways you can kind of energize it or add currents. Have you looked at that at all?
Globally, absolutely not. I didn't look at it. Yeah. I think locally we have attempts. That's
So I think that's something to bear in mind, that up to a point, and there's going to be sometimes where it won't converge simply because there's going to be information there which is not.
is missing. Yes.
Right, exactly.
Yes, but that's also information.
That's also information.
Yes.
Yeah, that's right.
Yes, and that's it.
So we have time for questions. If there are more questions?
An ultimate slide there when you were
Oh.
saying about your feet, when you bring it back up.
Okay.
But you see, you shouldn't expect all of the emission from a line to come from its peak formation temperature. Maybe
Yes.
elsewhere. It's not really a surprise, is it? Right? If you look at the contribution function of any line, there's
I know,
no
but
width to it. So
But even in this room, many people associate lines to temperature, and that's why and that's why I keep repeating this, because I think it's very important that we change the narrative. That's what I'm thinking. So just because you look at one line, you don't look at one temperature. That's Yeah.
Especially with SDO.
So, yeah, I was going to ask you to can you pull back up next to the last slide again? And you kind of, sorry.
Go ahead.
Yeah, do you mind sharing your last slide next to the last slide again?
Yes.
Kind of, I wanted to see the point that you were making with that one more time. Yeah, I think it's related to what you just said, but I just wanted to visually look at it and see how you guys simulated the line of sight emission for.
Or this? Or which one?
That's a blank slide.
Oh, I'm sharing the wrong.
There are two different points. STO is broad enough that there are more lines inside the bandwidth. And I just make the point that even for narrower.
Yep.
Which one? Which one you mean?
This one. Yeah.
There are not just one.
But-
There are two issues here.
Or this?
14. Yes, that one.
Okay.
What was the question? I'm sorry.
The question was, I wanted to ask her again to step me through what they did on this, what you were showing on this slide.
Oh, so here what I showed, that I calculated the emission in the 3D field, and I took the emission density, so I didn't integrate it, and I took the same value and drew an isosurface around the sun, and and I colored the isosurface with electron temperature, just to show that the same emission amount corresponds to different temperatures. So you have a temperature range that you consider
Right.
when you look at emission. Yes.
Yeah, thanks.
Yeah, thank you.
Any more questions? If not, let's thank Judith.
There's something.
Jamie, did you have something?
Oh, I
You have a microphone today.
Yes, I do have a microphone today.